Welcome to Introduction to Cryptography. For the first episode, we will learn finite field together. Let's begin our journey into finite fields by introducing a simple yet powerful mathematical function, f. A mathematical function is like a ruler machine. It takes each input from one set, called the domain, and produces exactly one output in another set, called the codomain. In our example, the function's domain is the set of all integers. The codomain, however, is much more intriguing. It consists of 11 distinct symbols, 0, 1, 2, and so on up to 10. These aren't just ordinary numbers. They belong to something special, a finite field of size, 11. Soon we'll uncover why this structure is so important. Returning to our function, let's bring it to life by visualizing the domain and codomain. To make this clear, we'll use colors. Green represents the domain, the input space. Red, on the other hand, represents the codomain, the output space. Notice how the domain is drawn as a straight line, while the outputs form a circle like a clock. This is not just artistic choice. There's a deep reason behind it, which will soon be revealed. Now let's refocus on the definition itself. Our function is defined as output equals input modulo 11. In simpler terms, divide the input by 11 and keep only the remainder as the output. For example, if the input is 0, the output is also 0. With input 1, the output is 1. But here's where things get visually exciting. Addition is represented as a counterclockwise rotation on the circle. Pretty cool, right? Let's keep going with more numbers to see the pattern unfold. As we keep increasing the input, the rotation continues counterclockwise step by step until we get to 11 and the remainder of the division of 11 over 11 is 0 again. By reaching 11, we did complete a full cycle and return to the starting point. Even if we go to 12, 13, or higher, the output always stays within 0 to 10. Now let's decrease the input and see what happens. As expected, subtraction turns into clockwise rotation on our clock-like diagram. What if we decrease the input further into negative numbers? Surprisingly, nothing breaks. You cannot get out of the set with addition or subtraction, no matter how hard you try. This remarkable structure is called Z11, the finite field of size 11. A field is a special set of numbers that remains closed under addition, subtraction, multiplication, and division. Mathematicians say a set is closed when no matter how you operate within it, the results never escape the set. We've already had a glimpse of this behavior. In short, addition and subtraction always keep us safely inside the boundaries of our finite field. The case of division is a bit more tricky. We will learn it in the next episode. But first, let's see a few addition and subtraction examples in Z11. Let's dive into some examples of how addition works inside a finite field. What happens when we add 7 and 5? To answer, we'll turn once again to our magical clock. We assign a color to each addition operands, orange for 7 and blue for 5. Now think of 5 as 1 plus, 1 plus, 1 plus, 1 plus 1. Just a moment ago, we discovered that adding 1 in a finite field means making a single counterclockwise step on our magic clock. So, starting from 7, we rotate 5 steps counterclockwise. Where we land is the result of adding 7 and 5 in the finite field of size 11. And yes, you guessed it, the answer is 1. Let's approach the same problem from a different perspective. This time we'll break down both 7 and 5 into sums of ones and see what unfolds. We start from 0. 0 is a neutral element of addition. Then we add ones, one by one. Initially, we cover all ones representing 7, and then we will go for the 5. However, it does not really matter which number we cover first. we will get 1 as result again, as you guessed. Let's redo the calculation using another approach, and I promise you this is the last time. Let's rewrite 5 and 7 as 1s, but this time let's group up every 11 ones. Why? Because 11 is the size of our finite field. And if we rotate 11 times, we get back to the same number. After removing packs of 11, we will add the remaining 1 to it, meaning we will rotate counterclockwise once. There we land again on surprise, surprise, 1. Now let's look how we can subtract two numbers in finite field of the size 11. In this example, we try to find the answer to 12 minus 15. Let's bring out our magic clock again. We will again use two colored lines to represent which values we are covering in summations. This time we use the shortcut that we learned in the previous part. We write 12 as 11 plus 1 and 15 as 11 plus 4. Well, rotating 11 times will put you back to where you have started regardless of the direction of the rotation, so we can remove each of these 11s. Note that we are not canceling them out. Each 11 equals to 0 and z11. Now it is much easier to find the answer. We have to start from 1 and rotate clockwise just 4 times to get to the result. The result is 8. Note how finite fields allow us to shrink both numbers and computations. With nothing more than addition and subtraction inside a finite field, we can already encrypt messages with the elegance of ancient kings. You might ask, why would kings even bother with this mathematical puzzle? Well, imagine being Julius Caesar, the famous ancient Roman king, needing to send secret battle plans to one of his generals at the front line, a message that could change the fate of an empire. What if some enemy troops find the messenger and read the message? What if the messenger himself reads the message? To protect such secrets, you need a mechanism that ensures only the intended receiver can read the message and no one else. So that's why we have Caesar Cipher. Cipher means encryption. Caesar refers to Julius Caesar. Caesar Cipher is an ancient encryption technique famously used by Julius Caesar and many others. Its magic lies in the simplest of tools: finite field addition and subtraction. To make it work, we step into a finite field of size 26. That means adjusting our magic clock to fit the alphabet. So we enlarge our clock, marking numbers from 0 through 25. Caesar encryption is nothing more than a shift. It simply adds 3 to the input. For example, to encrypt the number 3, we take our expanded magic clock and apply the rule. Just as before, we rotate counterclockwise, 3 steps this time. The result lands on 6. Now comes the true brilliance. Let's map numbers to letters. 0 becomes A, 1 becomes B, and so on, until 25 corresponds to Z. Suddenly, the cipher turns numbers into characters, and characters into secrets. For example, D transforms into G. Just like that, a letter becomes encrypted. To encrypt a whole word, we do this letter by letter. Take the word crypto, for example. We start by encrypting C to F by 3 counterclockwise rotations. Then we rotate 3 steps counterclockwise from letter R to encrypt it to the letter U. Then, using the same technique, we encrypt letter Y to letter B. Using the same method, we can encrypt the remaining letters. And so on, we encrypt all the letters one by one. The word would be encrypted into FUB-SEWR. Decryption mirrors encryption. Instead of adding 3, we subtract 3, meaning we rotate 3 steps clockwise. Applying this to FUB-SEWR brings us right back to the original word, crypto. After all, that's the entire point. We begin by decrypting the letter F, which is simply the inverse of the encryption function, giving us C. Next, by rotating 3 steps clockwise from U, we arrive at R. Using the same method, we can decrypt the remaining letters. Congratulations! You've just mastered your very first encryption scheme, the Caesar Cipher. For practice, you can pause and try decrypting this legendary line once spoken by Caesar himself. The Caesar cipher belongs to a larger family of ciphers known as Symmetric encryption. Remember how we decrypted by rotating 3 steps backward, the exact same number of steps used for encryption, just in the opposite direction. That perfect balance is what gives it the name symmetric. Let's take a closer look at the Caesar cipher's encryption and decryption functions. Notice how encryption and decryption mirror each other. They share the same structure and the same values, only applied in reverse. In symmetric encryption, the same key drives both processes. Anyone holding the key can perform both operations, encrypting and decrypting the message. Caesar cipher is an ancient and outdated encryption system. It offers no real security in the modern world. Among others, Caesar cipher belongs to a class called shift ciphers, where each letter is shifted to the alphabet by a fixed number of positions. Shift ciphers were among the earliest forms of symmetric encryption. Today, far more advanced methods are used. Well done, my friend. You've dipped your toes into the vast ocean of cryptography. In this round, our goal was simply to explore the core ideas behind cryptographic concepts. This is simply a node. Thanks for being here, and I'll see you in the next episode.